Okay, we have two attendees, three. Eric, so I don't know how to do that. So I have to change from the attending to panelist.
Yes. From the
How
chat.
I can to promote to the speakers.
If you put the pointer in front of the name, you can see that you have a menu.
Okay, got it.
And then you can change to, what is the name of the action? There's a change role to panelist.
Promote to panelist. Okay, got it. Thank you.
And the same applies if you want to downgrade from panelist to attendee.
Okay. And then I downgrade to attend it. Okay. Hi, Paco, how are you?
Hi.
Did you take your lunch?
Yes, what about you?
Excellent, great. I ate a big chile relleno, a big one. I like it.
Evitaré cualquier albur en este momento porque es muy
No. I ate by myself, so I like it a lot. Because there is a restaurant close on my house, and they sell chile rellenos and different kind of meals. So I bought one and I ate before to the Congress. So
¿Cómo se llama el restaurante?
actually, I don't know the name. Just arrived and pick up the chile relleno and pay it, and that's it. And I leave.
Good.
Okay, excellent. So we have, okay, Jose Alejandro, I promote to the panelist. Okay. Right now. Can you hear me, Jose?
Okay, this moves tricky. Okay.
Yeah, can you hear me? Okay,
Good.
how are you? Good?
Really good. Yeah, really
Excellent.
excited. Yes.
Perfect. So just, I guess, 1 minute more, just to more enter to the session. And I will start. ¿Sale? Okay?
Yeah, sure.
Excellent. So maybe it's good if you can start to share your screen.
Yeah, sure.
Try to do it.
Okay. Is this good?
Excellent. Yes, I can see it.
Okay.
Okay, I guess it's good to start now. So hello everyone. We are going to start this session of the International Complex Science and Technology Congress. In this session, we have 4 contribute talks. The first one is it will be given by the speaker, Jose Antonio Rivera Moran. So Jose, you have 20 minutes to get us to presentation, and I guess we have 4 minutes for some questions. Thank you so much for your presentation.
Thanks for the presentation, and hello everyone. I am Jose Alejandro Rivera Moran, and I am really glad to present at this conference recent work, which has been published already, that is about the implication of colloidal surface morphology on the near wall dynamics. So let's begin. I think, sorry, this doesn't move. Okay, So firstly, I would like to point the structure of my talk, starting with a brief introduction. Then I present experimental methods with their respective results. Later, the methodology of the numerical calculations with the corresponding results. And finally, I give some conclusions of the work. So just to get in context, when a colloidal particle approaches an interface, specifically a water glass interface, the particle's movement is mainly influenced by hydrodynamic and particle wall interactions. Brenner formulated a well-established model for the near wall dynamics of hard spheres close to the wall, and the diffusion of the particles becomes anisotropic. So it is discomposed geometrically in the parallel and the normal diffusion coefficients with respect to the interface plane. Regarding the colloidal particles, in reality, such particles are not as smooth as we commonly think. Here I show you a micrograph of a large lattice sphere where we can appreciate irregularities and the roughness on the surface. And we can think that maybe in the past, people had avoided this intrinsic roughness of the particles and maybe ignoring the possible effects that can induce. Here I comment two examples related to the implication of particle morphology in changes of the characteristics of that colloidal suspension. For particles with considerable roughness in suspension, the shear thickening effect is shifted toward lower volume fraction. For porous shell particles in suspension, people had seen that there is a reduction in the flow resistance in comparison to the sphere colloidal particles. So how the surface characteristics affect the near wall dynamics of these kind of particles? Hydrodynamic theory predicts that particles experience a faster near wall diffusion than spherical particles of the same outer radius. This could be attributed that a hydrodynamic penetration length will reduce the size of the particle and will reduce the wall drag effect. So in this work, we test this prediction experimentally by analyzing the near wall dynamics of colloidal particles with different surface morphology and supported with numerical calculations. So for the experiments, we use the silica particles shown here. One sample had a smooth surface, another has rough surface, and also we use hollow shells. We acquire the near wall dynamics by using the evanescent wave dynamic light scattering technique. This technique works as follows. A laser beam is totally internal reflected at the interface. So the particles that are close to the evanescent wave spot scatter the wave in form of light, which is then detected and later correlated. The evanescent field strength decays exponentially, and its penetration depth is defined according with that equation that is shown there. And also the scattering vector is geometrically decomposed in parallel scattering vector and the normal scattering vector according with those equations. Then to develop the parallel near wall dynamics of the particles, we acquire the intensity of autocorrelation functions from an initial Q parallel value to a final Q parallel value, varying the detector's position, along theta angle, and the Q normal remains fixed. Then we calculate the field autocorrelation function, and we determine the initial slope of the decay at each Q parallel. After that, such gamma values are plotted versus Q parallel, and the linear slope is the average diffusion coefficient parallel to the wall. We repeat this procedure for different penetration depths in order to get the near wall dynamics trend. Here I present the experimental near wall dynamics of the different silica particles along the parallel plane of the interface. In the left side are the parallel diffusion constants, which are normalized by their bulk diffusion constant. In the x-axis is the penetration depth, normalized by the bulk hydrodynamic radius. Also in the graph, it is included a hard sphere prediction as the reference model. So what we found was that the near wall dynamics of smooth particles is more or less close to the hard sphere model, just excepting for the value that at large penetration depths. The dynamics of hollow particles, it follows the trend of the hard sphere model, but a little bit slower, also excepting for the value at large penetration depth. But when we look at the near wall dynamics of the rough particles, it exhibits even more slower dynamics and with different trends. With these results, it is contrary to hydrodynamic prediction, where it expects a reduction in the wall drag effect and thus an increase of the near wall dynamics. So in order to elucidate which mechanism is under this behavior, we explored the possible considerations that might strongly influence the near wall dynamics of the rough particles, such as interaction between particles and the wall, polydispersity, and aggregation effects. So now we enter into the numerical calculation part. In the following slides, I'm going to present the implemented numerical method for the considered effects, and then I show the respective results. I start with polydispersity effects and then continue to particle aggregation, and in the end with the static particle interaction. So numerically, the initial slopes are calculated based on the equation shown here, which can be reduced when we consider monodispersed particles. Due to the limited time, I quickly show you that the average diffusion constants are computed by using the following expressions and approximations. When we address the polydispersity, this expression is no longer valid, since we add the particle size distribution factor, and the expression turns into this new equation, which it cannot be simplified as before, since it averages over the particle sizes. So for polydispersity, we consider a Gaussian normal distribution with a mean value mu and standard deviation sigma. When we consider aggregates, we consider a bimodal distribution, and the factor of the near wall form amplitude, which is the V, depends on the size and the shape as following. For the smooth particle, we consider a sphere under evanescent illumination. For the hollow sphere, we model it as a core shell. And for the rough particle case, we assume it as the sphere and the shell with a very thin thickness. So in a large picture, what we saw for the polydispersity effects on the near wall dynamics related to the smooth particle, the variation of the mean size distribution as well for the standard deviation, they don't affect in general the behavior of the near wall dynamics as compared to the hard sphere prediction. For the hollow sphere, we also didn't see any transcendent changes on the near wall behavior. And for the rough particle situation, we assumed similar results since it was considered as a sum of both cases. So the main message here is that polydispersity has a minimum influence in the near wall dynamics, and it can explain the observed trend as we saw for the experiments for the rough particles. Then we look for the particle aggregation. Here we consider a bimodal Gaussian distribution where the main population takes sizes of 100 nanometer. First, here we explore the effect of the size of the minor population. And what is clear is that aggregates plays an important role in the near-world dynamics. When we increase the population size, the changes of the dynamics become slower and slower. But when we looked at one curve and just varying now the volume fraction of the aggregates, we also saw a strong influence on the dynamics. But if we observe this carefully, the trends of the dynamics follows more or less the hard sphere prediction. So for us, what we get from this is that the presence of aggregates influences the dynamics, certainly, but the trend is still different of what we saw for the rough particles in the experiments. So we continue to see what's going on when we consider the static particle wall interaction. For the numerical implementation of the interaction potential, we consider that such potential is formed by three main contributions: the attractive van der Waals, the electrostatic repulsion, and the gravitational potential. For the van der Waals interaction, we use the expression for the sphere wall geometry. For the electrostatic repulsion, we use the linear superposition approach by Lind et al. This model considers an electrostatic amplitude, and it contains the electric properties of the medium and the surface potentials for the particle and for the wall. And for the gravitational potential, we use the well-known expression for such potential. So let me show what we got from the effect of the static interaction of the near-world dynamics. First, we looked into the influence of the electrostatic repulsion on the near-world dynamics by increasing the magnitude of the electrostatic amplitude. Here, all the curves at small penetration depths, the dynamics are smaller than the hard sphere line. And for large penetration depths, the dynamics become faster, indicating the repulsion. The crossing point over the hard sphere line depends on the electrostatic amplitude value. On the other hand, when we tune the Hamaker constant values in order to get attractive potentials, we clearly saw a strong impact on the near wall dynamics, and all curves are below the hard sphere line. As increasing the Hamaker constant, we can appreciate the reduction of the dynamics. And from certain values, the trend is similar to the behavior of experimental dynamics of the rough particles. So from here, we established that the particle wall interaction are the main variable that changes the near wall dynamics. Finally, we made the comparison between the experimental near wall dynamics of the particles with numerical calculations. For this, we include a bimodal Gaussian distribution, like modeling small aggregates. Also, the excess mass of density to consider a little bit of sedimentation, and the experimental Debye lengths. In the table are shown the values of other parameters needed to closely match the experimental near wall dynamics with the model. If we look into the graph, we can see clearly that the smooth particles and the hollow particles share similar near wall dynamic trends within the experimental error. And for these two cases, they also have similar values of the electric amplitude and Hamaker constants. But nevertheless, the computation of the closest values to match the experimental near-wall dynamics of the rough particles, the Hamaker constant needed to compensate this behavior was an order of magnitude larger than the other particles. In the table, I highlight these constants. So this implies that surface roughness plays a major role for the particle-wall interaction and thus the resulting near-wall dynamics. To finish my contribution, I give the main ideas that you can rescue from this work. The conclusions related to the experiments, we found that smooth silica particles and hollow silica particles follow somehow similar dynamics as the hard sphere prediction. And for the rough particles, the near wall dynamics is drastically slower than the other colloidal systems. And this behavior is in conflict with hydrodynamic predictions. So we implemented numerical calculations in order to explore the near wall dynamics due to particle polydispersity, aggregation effects, and static particle wall interaction. In this direction, what we get from the numerical calculations is that polydispersity has a minor effect on the near wall dynamics. When we consider aggregates, they affect the near wall dynamics by making such property very slow, but the behavior is still similar as the hard sphere trends. And for the particle wall interactions, we saw that Hamaker constant is a main property that contributes to the reduction of the near wall dynamics, as similar trend of in the experiments. And in the third part of the conclusions, and for the third part of the conclusions, we saw the small silica particles have dynamics that are similar to the hard sphere prediction, and the related parameters values has physical meaning. For the case of the rough particles, for the case of the rough particles, there is an enhancement of the van der Waals attraction that comes from the presence of the asperity on their surfaces. And our findings follow simulation reports that relate the asperities with the reduction of the stabilization barrier in the DLWO potential, which is translated to accessible space at short distance from the wall. And finally, our results suggest that rough particles wall interaction potential overcomes the hydrodynamic contributions, resulting in the reduction of the near wall dynamics. And this is all for me, and thanks for your attention.
Thank you so much, Jose. Very, very interesting talk. So we are open to some questions from the attendants. No? Okay, we have a question from Paco.
Yes. Hello?
Yes.
Jose, can you hear me? Yes.
Sure.
Yeah. Thank you, Jose, for your presentation. I was wondering about this big conclusion that you said about the roughness and the hydrodynamics interaction that are reduced because of this roughness. But as a matter of fact, do you have a way to measure the roughness of your particles?
Well, this is an important part of this project. So these particles are kind of special because people who synthesize these particles, they have a well-established protocol to make these particles. So they say that they can prepare these particles with more or less the same ratio of asperities and the asperity size. and well, we rely on that
But this
there
is
is
not a,
more or
this
less
is,
controllable.
sure,
Sorry?
sure, but this is not, yes, but this is not a measure of roughness, right? So, I mean, you have a kind of rough particles, but in the sense that to see whether the roughness implies a reduction of the hydrodynamics interaction, you need to have more particles with different roughness, you know? Because what you are saying is independently of the roughness, you will have an attraction with the wall. That's what I understand. Maybe I misunderstood something.
Yeah, sure. No, sure. And I agree with you. And well, at that moment, the only available particles were from that batch. But sure, I mean, for further complement research in this direction, should be testing other rough particles with another degree of roughness. Yes, but at this moment, I can say more about how these changes will influence the dynamics.
I see. Okay. Thank you, Jose.
Yeah, thank you, Paco. Oh, Eric?
Well, Alejandro,
Hi, Eric.
it's great to see you and nice work. In the same way as Paco, I'm wondering about the roughness, not only the particle, but of the surface. I mean, if this effect is related with the roughness, should apply to the surface of your glass plate below. In that case, you may, you, for example, can compare your results of particle that is with some roughness and the glass plate is completely plain, to the opposite way, that you, where you use particles that are quite smooth, but maybe you can try to make some roughness on the glass plate. That may cause some scattering, but I'm not sure if that can also be used to compare and be sure that is related with roughness, with the roughness of the either the particle or the glass plate.
Yeah, yeah. Also, there is an important point. The sample cell that we use is a polished glass. I don't remember the details, but in practice, people claim that is almost smooth. But in experiments, we also can detect some scattering that comes from that surface, and that scattering also is taken into account in the analysis procedure. So we are maybe 99% sure that what we are acquiring experimentally is due by the particles.
Yeah, of course, great. And I don't know if you remember that once we were discussing with Jose Luis Arauz and Said about the possibility that maybe some absorption of of very small polymers can affect also the hydrodynamics. And now that you've been studying this for a couple of years or so, do you think that, for example, the presence of a small particles, small polymers attached to the glass plate can actually modify the hydrodynamics? I mean, only the hydrodynamics. Of course, there may be some interaction between the polymer and the particle, but only the hydrodynamics can be affected by the presence of this, maybe polymer or so attached to the glass plates.
Okay.
Of course, it's a different topic from yours, but that's I told you, maybe after a couple of years of studying this kind of interaction, you may have some answer of that questions that arise maybe 4 years ago in San Luis Potosí.
Yes. Well, I'm not sure about what to expect about having another molecules around in the suspension that can influence the hydrodynamic contribution. But what can I tell about the preparation of the experiments? The colloidal suspension were prepared in a clean space, and as well the procedure for the cleanness of the sample cell also. We don't use any soaps or any additives to clean that sample cell. I mean, we only use water and this ethanol, acetone that in the laboratory has been used several times without any contributions.
Okay. Thank you, Alex. Good to see you. Thank you, Julio.
Thank you, Eric. So I guess it's enough time for questions. Thank you so much, Jose, for your presentation. It was so interesting. So now we are continuing with the next speaker, Fernando Donado. Please, can you hear us?
Yes, I can hear.
Hi, Fernando. How are you?
Fine.
Excellent.
Glad to see you.
Nice to see you too. So now, could you share us your screen?
Yes. Someone is sharing his screen, so I need to turn off the other participants.
Okay. I guess. No, we are not. Jose, we are seeing your screen yet, so you can stop.
Sorry, okay.
Yes.
I'm sorry.
Excellent. Thank you. So, Fernando, try again.
Yeah.
Yes, we can see now. Okay, Fernando, you can start, please.
Okay. Good afternoon. It's my pleasure to present our field results in our study of vortices in an active matter system based on magnetic bead under an alternating magnetic field. This is in collaboration with Maria de Los Angeles Escobar, who is my PhD student. Our experimental setup to study vortices in active matter consists of a non-vibrating granular system. This is composed of many magnetic particles that are under an alternating magnetic field. This magnetic field fluidizes particles by the following mechanism. Each particle has its own permanent dipole moment, which is aligned with the magnetic field. When magnetic field reverses direction, the dipole or the particle try to align again with the direction of the magnetic field. So it's easy for the particle to rotate. It's easy because it's a sphere and has a neutral equilibrium. So while the particle rotates, it's rolling over the surface because of the gravity and the friction. While you're rolling, it describes linear trajectories. When magnetic field reverses direction against the particles, over the particle acts a new impulse that makes the particle continue rolling in the same direction or maybe change the direction in a random way. This system is an active matter because each particle takes energy from the magnetic field and transforms it into kinetic energy. So the particle move around this possible space. In the past, we had used this system to study glass transition and crystallization. So, but now we want to share some new field of study with this system. Here is a video. I hope it is okay, the transmission of the information. Here is a video. The magnetic particles are moving around. This is in a small temperature, effective temperature. Here are the trajectories in this system. We cannot observe any vortex. So it's normal, it's very normal. However, when we increase the effective temperature, increasing the magnetic field, we observe the creation of a vortex, a huge vortex. Maybe here is better visualize the vortex, and this is the object of our study. We have carried out different experiments, changing the container sizes, the amplitude of the magnetic field, and the shape container. So in order to characterize the motion, we determine the mean square displacement. And as we expect that this mean square displacement reach a plateau, and as we can see from the trajectories, we expect that is not the particles are not diffusive at all. We will feed the data to a power law. It will be determined the alpha parameter. When the alpha parameter is lower than the unity, the motion is subdiffusive. When the alpha parameter is equal to the unity, the motion is diffusive. And when the alpha parameter is greater than the unity, the motion is super diffusive. So here are some mean square displacement curve. And we observe that at a higher magnetic field, the particle reach saturation very fast. For a smaller temperature, the behavior is a little, the dynamics is slower. And in the Windows time, we determine the mean square displacement. They do not reach the plateau. So in the figure of in the right side, below the right side, we observe the fitting to the power law of the data that are in the shadow, in the blue shadow rectangles. So we, as I told you, we fit using a power law. Here is the results. The alpha parameters versus the amplitude of the magnetic field. We observe a continuous transition from a diffusive motion to a super diffusive motion. The vortices are formed when the particles develop a super diffusive motion. Here are some diagrams obtained by the technique of particle imaging velocimetry, where this allow us to observe the formation of the vortices. We can observe also that these vortices are not completely closed, but are evolving. In the center of these vortices, particles move slowly. Also outside the vortices, the particles move slowly. So we also characterize this system by finding the coordination number and the 6-bond orientational parameter in order to look for insights in this system. This is a video. In each particle is colored according to the nearest neighbor that are in contact with the particle. We observe some particle fluctuation, particle concentration fluctuation, and we cannot observe the formation of permanent aggregates. So it seems there is not order in the long correlation distances. The fast Fourier transform also tell us that the system remains disordered. Next to this fast Fourier transform image is a video with aggregates in these systems. We observe the formation of aggregate, but this aggregate lasts very short periods of time, so there is not a formation of aggregate. There is not a formation of long distance ordering. We had also obtain these vortices in a smaller container. Here in this video that I hope you will appreciate the motions, most of the particles, practically all the particles are involving in the vortex, except the particles that are near the boundary. Here are the same video, but we depicted the trajectories. And as I told you, all the particles are involving in the motion of this vortex. So we expected that as the smaller the container, the vortex will be better. However, we found this interesting observation. For the smallest container, the vortex is not formed. So here observe the trajectories of each particle. So until here we can conclude something interesting. To develop a vortice in this system, the condition to be bonded, the system needs to be bonded. However, if the boundaries are too close, if the container is too small, there is no formation of vortices. As I told you, we had also carried out experiment changing the recipients, and here is a square recipient. And also we observe the formation of the vortices. In this case, the vortices is changing. It is not totally stable, and the center of the vortex is moving. If we observe the movie at long time, we observe the center of the vortex is moving in the horizontal direction. And here we observe the trajectories of typical trajectories in this system. We observe the vortex has ellipsoidal shape. So in this case, the vortex also is formed in hexagonal container, except that here the vortex is very unstable. In the long time videos, we can observe the formation of a vortex, but very often this vortex is destroyed and reformed again. So comments until here that the vortices are formed under confined condition, high particle concentration, and high temperature. This system, although the system is highly dissipative, the continuous energy input prevents particles from stopping. This system is not in thermal equilibrium, but it is in a stationary state. So it meets the condition to be considered an Oster-Uhlenbeck stochastic process. So what we continued in our study is apply most of the usual tool from the mechanical statistics to describe this system, because in the past we also have shown that this is a good recipe when the system is in a stationary state. Thank you for your attention. Here are my contact information details, and this work has been done by my student, my PhD student, Maria de los Ángeles Escobar, and that is her email. And I will be very glad if you had any question. Okay, that's all.
Perfect. Thank you so much, Fernando, to show us the very interesting results and videos. So we are open for some questions for attendees or panelists. Okay. Well, I have some questions. One of them is, maybe I lost a little bit. What is the reason that you have in the system is more dense in the low part? It's like the gravity, or which is the reason? I don't know if you come back one of your videos.
Yeah.
For example, there, why you have is more dense in the low part of the circles. I mean,
yeah, yes, the system is slightly tilted in order to create a particle concentration gradient.
Okay.
We had observed that under this condition, the vortex is more stable than in the completely horizontal conditions.
Exactly. Yes. Yeah. And yeah, actually, I have another question. So you're studying so your system is homogeneous in the density. I mean, what happened, or did you try to change the density? I mean, if I increase the density, how much or why? What is the density in these systems, more or less, or the packing fraction?
To tell the truth, I didn't measure yet. However, we had a series. Currently, we are working with this system, and we have carried out experiment changing the particle concentration. So in a future talk, I will talk about the results about changing the particle concentration.
Okay.
I can tell you that there is a limit in the particle concentration. Below that, there is not a formation of vortex.
Okay, yeah, maybe I expect that. So, and another question is, what is the effect to increase the size of the cycle? I mean, it's better in order to make easier the vortex, or if I increase or reduce the cycle. Did you try that?
Yeah, yes. In fact, I show you three different size container. This is medium. This is a medium size container.
Okay.
And here is the smaller one.
Yeah.
For the smaller one, there is not a formation of vortex.
Okay.
From previous experiment, we know that if the recipient is big enough, there is not also there is not the formation of vortex. So there is a size that is ideal.
More or less, what is the ratio between the size particles? I mean, this is like
the size particle?
Yes, so the ratio
1 millimeter. 1 millimeter.
Okay. Perfect. Thank you. Another one? So has a question?
Yes, Julio, please.
Okay, Victor.
Okay, thank you. Okay, hi, Fernando. How are you? Nice to see you.
Hi, Victor. Nice to see
you. Thank you very much for your presentation. Yes, I think it's a wonderful presentation. So I have a little question. Could you explain what is the main problem to perform this kind of experiment in your laboratory? So general, please. I see every day working a lot. So could you explain what is the main problem to perform this kind of experiment in your lab?
Particularly with this experiment, there is not a big problems. Maybe the most challenging problem is to get the particles. In the laboratory, there are many problems, no? Mainly because of the lack of resources. So happily for me and for my group, this experiment is very cheap. Happily for us, give to us the opportunity to contribute in my humble opinion, in very high. I mean, we had produced knowledge that is in the first level, although the system is very, very cheap. This led to okay. Your question makes invite you everybody to replicate this experiment. It's very easy to replicate, and we can study many systems. Today, for example, in the talk of Ruben, he studied some Brownian particles in a double well, for example. Here with this system, we can do that very easy. So it's an open invitation to collaborate with us, or even to replicate in an independent way that system. Of course, we always wanted to do experiment with other resources, no? But maybe in the future. Thank you, Victor.
Thank you, Victor.
Thank you.
We have another question from Paco.
Yes.
Thank you, Fernando. So you said that you think that these particles move as Brownian particles?
Yeah.
But then, since you mentioned that you have active matter, what would you expect if with active Brownian particles with that density is that you observe motile-induced phase separation? What is not the case? I mean, you have these long correlations given by this vortex. Maybe this should be because of the form that you make the movement of the particle, that is by an external field. So probably this is in fact actuated particles, not active particles itself, right? What do you think about it?
Please restate your question, because I lost some of the audio.
So what I was wondering is that these particles are really Brownian, active Brownian particles, because it seems to me that since these particles need an external field to move, it seems that for me these particles should behave more like actuated particles than active particles. Therefore, because actually if they are active Brownian, you should see motile-induced phase separation, but it's not the case. I mean, what you observe is these long correlations given by the geometry of the system, not even with an alignment interaction. It's just because of the geometry of the system, right?
Okay, let me tell you the following. Under some condition, the system is particle describing motion like a Brownian motion, and we can observe that there are signature of that in the mean square displacement. Yeah. In previous work, we have showed that a short time the motion is ballistic, at a long time the motion is diffusive under certain condition. So in the experiment that we present today, we use a high temperature that we had never used in the past. So in this case, we had observed the formation of these vortices. It's a new phenomenology that we can observe in the system. Also, under confined condition, for example, in a circle, in a circular track, we also observe the behavior. That the behavior is super diffusive. Okay. In the vortex, the motion is super diffusive. In confined condition, the motion of this particle is super diffusive. So it's not Brownian, but it's super diffusive. But under other condition, the motion is Brownian at a lower temperature. On the other hand, the definition of active matter, as explained to us panelists such as Arezzo, Francesca, is an active particle, an active matter takes energy from the environment and converted it into kinetic energy to explore the whole region. Yeah. So this continuous taking of energy and let to the particles move around all the time. So that is the definition of active matter.
So granular matter is active matter?
What?
So according to that definition, granular matter is active matter, no? When you put if you shake granular matter, what you have is active matter?
No, all the granular matter. Not all the granular matter. Actually, currently there is in the community, there are, it is a question that is open. And I had heard about these discussions. And at least for this system, I can show you many experiments that which with them I can argument to you that is an active matter because it meets the condition that I may share the characteristic of active matter. Not all the granular matter we have like this. However, in this case, it meets is that criteria of active matter. Whatever the argument you could say, I can agree that.
Okay.
Okay, thank you.
Maybe in some moment, I would like to do that because I like to argument this kind of phenomenon.
Yeah, sure, me too. Thank you.
Well, Victor, you want to say something?
Invite to Francisco to work in the lab with Fernando.
Yeah, I would love to. I mean, I already have some calculation of that. I mean, Fernando, we should talk, Fernando. Yes.
Okay. Thank you so much to Paco for the question and Fernando for your presentation and your results. Thank you. So now we are continuing with the next speaker, is Carlos Andres. So could you try, Carlos, share your screen, please?
Hello. Yes. Okay. Everybody can see my screen.
Yes. Yeah, you can do it. So you can start anytime.
Right. Hello, everyone. My name is Carlos Salinas, and in contribution with my advisor Abelardo, we developed the topic of my talk, which is hydrophobic solute encapsulation by amphiphilic microcrafted bottle brushes. Polymers are very diverse materials, among which we can find a special type of polymer called bottle brushes. Bottle brushes have different applications, but one special application is that they can act as drug carriers. And when they act as drug carriers, they can form micelles with different conformations, which can be spheres, cylinders, torus, vesicles, etc. And these micelles will dissolve into the human body, releasing a drug. Micelles can react to, bottle brushes can react to different external stimulus, such as high pH environments, temperature, or UV light, like in this example over here, in which we have a drug-loaded bottle brush, which in presence of UV light releases its drug. Also, geometry plays, the structure of the bottle brush plays an important role into the conformation of these micelles. Lue et al. Has found that for this polymer, which is PGMA, PAE, PLA, with this structure, when it's empty, it forms these worm-like micelles, like the ones over here. But when they loaded with hydrophobic drugs, they found that they collapsed into spherical micelles. But in another work of Garcia et al., they have found that for the same polymer, but with a different structure, and now this hydrophilic chain is much more longer, the polymer remains with this worm-like shape, and it does not collapse into a spherical ones like in this example over here, which indicates that the structure of the bottle brush have an important role into the formation of and into the geometry of the micelles. And this is the scope of our work. We are trying to see what parameters of the structure of the bottle brush plays an important role in this phenomena. But what is a bottle brush? A bottle brush is a polymer which has a main chain called the backbone, and side chains are coming out from it. And it features a high polymeric side chain concentration, an extended backbone due to the relation between the side chains, and a reduced space density due to chain entanglement. They have different structures, but the one we are focusing is the myctographic structures of over here, in which we can see that in one of the side of the bottle brush we have one type of polymer, and in the other side we have another type of polymer. And this one can be they are formed through a grafting process in which individual monomers or prefabricated chains join together to form a bottle brush. Now, we simulated these bottle brushes, and when it comes to the simulation, we have to take into account the time and length scale of our system. Polymers are usually simulated into the atomistic and mesoscopic scale. However, if we need to understand some other things, more specifically about the quantum structure of the polymer, we can use quantum mechanics as simulation techniques, or if we have a big system, we have to use continuum mechanics techniques. But the one we are focusing in this work is this one. Now, at the atomistic scale, we have molecular dynamics, which is a pretty simple but yet powerful simulation technique in which the position and velocity of the particles can be predicted using Newton's second law. And this is really useful when we have a relatively small number of atoms. However, when this number increases, also the number of calculations that have to be performed increases, and there is no computer capable of doing such number of calculations. For this, we had to coarse grain of our system, which means that now we group a bunch of atoms that have similar properties into just one single particle. And this single particle will react with another particles through interaction parameters, and this leads us our system into the mesoscopic scale. In the mesoscopic scale, we have simulation techniques such as dissipative particle dynamics, which is the one we are using in this work. Now, DPD is pretty much similar as molecular dynamics, as both of them are based into Newton's second law. But in this, DPD maintains the momentum of the system, and thus the aerodynamics is conserved. Also, the force between pairs is represented by a contribution of 3 individual forces that we got over here, in which this one is a conservative force that represents the exclude volume interactions. This one is the dissipative force, which represents the friction between the beads, and this one is the random force, which represents the stochastic forces of our system. And these forces are represented by these equations over here, in which this parameter Ij is interaction parameter between two particles or two species. It is related to the Flory-Huygens parameter as this expression over here. The Flory-Huygens parameter is just a quantification of how attractive or repulsive the interaction between a particle I and particle J is. Now, once that we have calculated the position of our system, we can calculate the gyration tensor with this expression over here, in which we have this is the position of a particle, and this is the position of the center of mass. And from this tensor, we can obtain the relative shape anisotropic parameter A3, which is a quantification of the geometry of our system, and this is obtained in terms of the trace of this tensor. As we can see over here, this parameter A3, this is an isotropic parameter for cylindrical micelles has a value above of 0.35. For ellipsoid micelles has a value between 0.35 and 0.15. And for spheres, it has a value less than 0.15, which means that the closer this value gets to 0, the more spherical our system is. Now, we're trying to replicate, so we're trying to understand the self-assembly of PGMA, PAE, PLA, which is a mixed grafted which is a micrografted polymer. And this was coarse-grained into these 3 bits over here, where the big bits represented by A are the hydrophilic chains made of PAG. The green ones labeled C are the backbone of our system, which is made of PGMA, and the blue ones represents the hydrophobic side chain made of PLA. Also, the drug, which in this case is doxorubicin, which is an hydrophobic anti-cancer drug, and solvent, water in this case, are represented by bits D and S over here. And the length of these side chains of the hydrophilic and the hydrophobic side chains were changed from 3 to 21 bits per side chain, leading to a bunch of symmetric and asymmetric systems. All this for 4 backbone lengths of 60, 120, 200, and 400 per backbone. Now, the repulsion parameters between the species were obtained from different sources, and they are shown here in this matrix. For each backbone length, a set of 49 systems were simulated, each one with a single board brush using HOMD Blue, visualized using BMD. And the relative shape and isotropy parameter was obtained using in the analysis. Our simulation box was big enough to avoid the self-interaction between the polymer, and we use periodic boundary conditions. Now, what we are saying over here is the results for unloaded micelles, and this is the case for a backbone length of 60 bits. In this figure over here, we have the morphology map in which the x-axis represents the hydrophobic side chain length, and the hydrophilic side chain length is represented in the y-axis. As we can see, if we can fix it, the hydrophilic side chain at a low value of 3, the system will get more and more spherical as the hydrophobic side chain increases. On the other hand, if we keep the hydrophobic side chain fixed at a low value of 3, as we increase the hydrophilic side chain, it will form cylindrical micelles. And from this morphology map and from a color map of the A3 parameter, we can see that in this region over here, a cylindrical micelle is being formed, and this one is represented over here. And from these 2 maps, we could build a phase diagram represented in this figure, in which we can see that most of the micelles self-assembled into spherical and ellipsoidal micelles. Now, if we increase the backbone length to 120, we can see that more and more cylindrical micelles are formed in this long A, short B region here. And even though a lot of the micelles self-assemble into spherical and ellipsoidal micelles. However, when backbone length is increased to 200, we can see more and more cylindrical micelles, all of them in this long A, short B region over here. And this means that in order to have cylindrical micelles, we need to have a symmetry in our system. More specifically, we need to have a long hydrophilic side chain and a short hydrophobic one. And we can conclude this from the results for when we increase the backbone length to 400, in which we can see that even more cylindrical micelles were formed in this, not only in this long A short B region, but also in the long A long B region. However, the tendency over here, we can see it as most the cylindrical micelles are from this area. Also, this means that increasing the backbone length, we also increase the number of cylindrical micelles in our system. Now, when we added drug into our system, for this, we chose a backbone length of 200, and we just choose this tree system. We change the hydrophilic side chain from 50 to 21, and keep the hydrophobic side chain constant at a value of 9. And we chose this system because if we can see here from the phase diagram of 200, we can see that these missiles over here are in the range that we are interested, because these are ellipsoidal and cylindrical. And what we wanted to study is the collapse from cylindrical and ellipsoidal missiles into spherical ones. And for this, we changed the concentration from 1 to 50%, and also we studied the evolution of the A3 parameter. Over here, we have the morphologies of the drug-loaded system, in which we can see that originally our system started as a ellipsoidal missile and two cylindrical missiles, and slowly it transitions into spherical missiles with concentration. And from this morphology map and the A3 parameters, we were able to build a phase diagram picture over here, in which we can see that for a concentration of around 9 to 12%, cylindrical missiles transform into ellipsoidal ones, and for ellipsoidal missiles transform from a concentration of around 23 to 30% into spherical missiles. Also, we see the evolution of the A parameter, and we can see that over here, our parameter falls slowly to a value close to 0 at a range of 20 to 30% in concentration, which is in concordance with what we have observed in the previous slide. Also, we obtained the drug-loaded efficiency with this equation over here, and we can see that the efficiency increases as the concentration increases, and it reaches a stable level over here, a concentration of 35%. This is pretty logical because the more drug is in our system, the more drug is going to be encapsulated. In conclusion, we found out that body brushes self-assemble into cylinders, ellipsoid, and spheres. There is a strong dependence of the number of cylindrical missiles assembled and the backbone length, and we found out that the longer this backbone length is, the more cylindrical missiles are formed. The morphology of missiles depends mainly on the hydrophilic side chain length, as we can see that asymmetry plays an important role, as we need to have a long hydrophilic and a short hydrophobic side chains in order to have cylindrical missiles, and increasing the drug concentration of these cylindrical ellipsoidal missiles will induce a transition into spherical missiles at a certain concentration. I would like to thank these institutions for the HPC resources and you for your attention.
Thank you, Carlos, for your presentation. Now open for questions. It's open for questions, please. No? Carlos, I have a question. Could you back your slides for the results? Would you show like a for N200, please?
This one over here?
Yes, more
14. This one?
No, 14, I guess. Yeah, that is one. It's for 400. Okay. Do you think that if you increase more the number of N, maybe instead of to have cylinders, maybe create like a torus structure? I mean, they connect in that way to, I don't know, to minimize the surface tension or something like that?
Yes,
because if you see, for example, when you have like 21 in A and 3 in B, so you have, when you say that you have a cylinder, but really they're a deformed cylinder. I mean, maybe if you increase more, you can connect between them in order to have a like a torus. What do you think?
Yes. This one over here we can see in the B3 and A21, which is like pretty much like a worm-like missile instead of a cylinder. I just said it was a cylinder because to simplify a little bit more the notation. But yes, I think we can, if we increase the backbone length, we will find more we will find torus micelles. And in fact, in one experiment that we did with PS, which is not pictured in this presentation, we found a toroidal micelle.
Oh, okay, good, excellent. And well, maybe one question more. What is the reason to use like the dogs? I mean, you change. Well, the first question is what is the reason to use like a dogs? I mean, it's possible to change in the backbone the molecules to have like a different effect. I mean, one like a dogs.
Well,
I lost a little bit.
oh, okay. Well, the system I'm representing here is
Yeah, you go back to the first or second slide, and yes, that is good.
yeah, the system we are representing over here is PMA, which is the backbone, and PAE and PLA, which are the sidechain, and DOX is the drug that we are using in our system. Well, we use DOX because it is an anti-calcium drug, and there's a lot of information about it. We have the fluoroadherence parameter for it with different species, and a lot of studies have been performed with this drug. So that's why we use drug. But in these studies that I present over here, in which we are basing our problem, they use another type of drugs that are RCB and PCB, if I'm not mistaken. Well, the thing is that both of them are hydrophobic drugs, and what we wanted to show is that the use of hydrophobic drugs will induce this behavior over here. Yeah,
Okay.
changing the drug will work with another hydrophobic drug.
Okay. Well, I have another question more.
Okay.
You're using a solvent, well, you're using a water as a solvent.
Yes.
I mean, the reason that you can make like a spheres is because the hydrophobic interaction, no, induce not the formation of the spheres. I do think that maybe that can maybe if you put inside of these spheres like some kind of another drug, no, and you can transport it and then change the solvent in order to open, and you can deliver that drug. Do you think that maybe it's possible to have a some application for this kind of system? What do you
Yes.
think? Do you think it's reasonable to think that, or?
Yes, yes. It can be performed. In fact, there are a lot of experimental and computational information about this change of solvent, and in which they have initially a solution of THC, no, THF, sorry, and they just change the concentration of this solvent, and they have a different behavior in the drug release system.
Excellent. Yeah, actually, my second question was how was the effect of the pH, but you first say about that. Excellent. So, anyone have someone has another question for Carlos? Okay. Well, thank you so much for your presentation. Very nice results.
Thank you very much.
Thank you. So we are continue with our next speaker is Ivan. Let me promote the panelist. Okay. It's a little bit. Okay, Ivan, can you hear us? Could you open your microphone?
Yeah, of course. Give me a second to arrange my screen.
Okay,
please.
Excellent. Yeah, we can see your screen. Yes.
Okay, you can see right
yeah,
there.
we can see your screen, and I can hear, and I can hear you.
Okay.
You can start.
Thank you so much. Well, good afternoon. My name is Ivan Pompa Garcia, and I will present you the work developed with, joined with Dr. Leonardo Dagdug, both of us at UAM Iztapalapa. And the title is Two-Dimensional Diffusion Based by a Transverse Gravitational Force in an Asymmetric Channel. Okay, let's start. Now, the outline of this talk is this. First of all, a short introduction followed by a brief description of the projection method will take us to our results. After, I'll show you how to use Brownian dynamic simulations to validate our theoretical results. And finally, the conclusions will be stated. So, the diffusion coefficient can be used to describe or characterize the transport in a system. And for a free system, usually diffusion constant or D0 is used. But if confinement or external fields influence is imposed, then an extended model where an effective diffusion coefficient is needed. In this case, in this particular case, the effective coefficient will be x-coordinate dependent. Okay? Now, this slide only shows 4 of the starters or pioneers of the diffusion study. The first 2 made contribution describing the phenomena, and the last 2 also developed theoretical or mathematical tools. Jan Ingenhaus wrote a description of coal dust immersed into alcohol. Robert works with pollen, and Fick stated 2 laws for quantitative description of the flux and also diffusion. And Jacob extends Fick's work to include the effect of the boundaries of the system. Now, this table works as a depiction of the diffusion coefficients and their applicability to different kinds of systems. It shows if they work in 2 or 3 dimensions, also if it can be used for systems with symmetric or asymmetric boundaries, if it is an effective coefficient or just a constant. And the last column, the last column here, presents if theory considers the influence of external forces. This last feature has been left out constantly, as you can see. Now, a really rough brief outline of the projection method. We can say in these points. Well, this was proposed by Kalinay and Perkus, and the first step is to write the 2-dimensional Smoluchowski equation. This time now is 2-dimensional, but could be 3-dimensional if the system that we're trying to describe has the same number of dimensions. Here, rho denotes the density function, but also can be understood or viewed as a probability. Next, it's the need of choose a potential, and for this particular case, we took a gravitational-like one, and a new variable, lower g, is defined, but this is just for convenience. Now, the equation 2 is a 1-dimensional or reduced density, and is calculated inside the system boundaries. And this could be a double integral if the departed point was to be taken the 3-dimensional Smoluchowski equation. It means that we are studying a 3-dimensional system. This is not the case. The easiest solution is the equilibrium solution. This can be found assuming that the bulk diffusion constant in the transversal directions tends to infinity, which means that doesn't matter if the random worker moves through the longitudinal direction, but the equilibrium across the y coordinate is restored fast enough to assume an equilibrium status. This equilibrium solution is denoted by rho 0. Okay? And this rho 0 contains also this function A. Now, function A is a normalization function containing information about boundaries and external potential. For simpler cases, that means without potential, it reduces to the Swansea case where the function A is simply twice the channel width. Having an equilibrium solution, a perturbation series can be considered if the expansion parameter is epsilon. This is the ratio of Vogel coefficients in both the spatial directions. But if we look closer, this also represents an anisotropy measure. Okay? After a lot of ominous calculations, and a key assumption is made. This is for long times, a stationary regime is reached. Then the D, the X, this case, the effective diffusion coefficient, can be found. This really rough and brief resume or summary about the projection method. Now, using this, we can obtain the next results. This is our main result of our work, a new effective diffusion coefficient. One interesting question about it became apparent from the observation of the second and third right-handed terms. I mean, this is the second one, and the third is in the lines 3 and 4. The second one contains information of the symmetric part of the channel. You can see right here. And meanwhile, the third terms talk us about the asymmetry of the system. In fact, if the channel is symmetric, Y0, so the mean line of the channel becomes null. Therefore, its derivative, it's also 0. Okay? So the midterm vanishes completely. These two last lines will be 0, will be null. And the second term reduces to the one proposed by Kalina himself for symmetric channels. Okay. Now, also, the equation 5, the last equation, can be written approximately as an interpolation formula. This has been proposed initially by Reguera and Rubí, which Kalina brings back for his work. And actually, if we took the Taylor expansion of this equation 6, the first two terms reproduce correctly our main result, where and the function eta is looking like this one. Okay. Also, we can see here that the asymmetry of the system is present in the second right-handed term, again present with the derivative of the midline term, y0 prime. Okay. Now, a couple of extras, right? If we assume that G is much less than 1, we can find this formula. From the previous 3 equations, we can arrive at this new Bradley-like equation for small values of G. We must remember that Bradley found an equation for asymmetric channels, and this can be recovered if we take this G constant equals to 0, and this is Bradley equation, as is. And from it, we can see that also can recover Swansea result if the channel is symmetric. That means y0 prime squared is null. So this generalizes Bradley result, but now for a small external constant forces, which he doesn't consider in any of his works. Second one. Also, if we remove the external fields from the interpolation formula, we can write this equation 9, where asymmetry and boundary information are present and the exponent and differ only by 1% from the Tattoo-Antineda equation for asymmetric narrow channels. They found a formula where trigonometric functions are needed. Now, what happened with Brownian dynamics? The validation of the approximated model we built was carried out by Brownian dynamic simulations. The channel shape was taken from the work of Burada and Schmidt because they arrived at a result coming from a momentum approach for periodic channels, which can be compared to a result, at least for symmetric case. Equation 10 was used for symmetric channels, and the symmetric ones were carried out replacing the lower boundary with a zero function. Now, the parameters of the simulations were pretty standard. As you can see in these slides, Vita, or the thermal energy, was taken to be 1, and the bulk diffusion coefficient is taken to be 1 also. The time step, it's a millionth of a unit. They took 10 to the 7 steps, so the total time for each random walker is taken to be 10. And external constants force was plus and minus g, and the number of particles went 2.5 times 10 to the 4th. And also this was simulated with 2D periodic channels, and the period is taken to be L equals to 1. And in the next slide, we'll see a figure that represents the channels. Now, this is our results. For symmetric case, these results of the Brownian dynamics, and in the inset figure, you can see a picture of the used channel. This is the period. The midline is 0 because the channel is symmetric, and we only use 1G, not plus and minus, because of the symmetry of the systems. We got exactly same results. So, the lines representing theoretical results are practically indistinguishable from each other, and the result obtained through the momentum method is also presented here. This is the reference number 1, and must be shown in red. I think it doesn't barely distinguish right here, maybe, but all of the theoretical equations and Brownian dynamics points are practically indistinguishable. This is for symmetric channel. Now, for asymmetric channels, the lower boundary was replaced by a constant, and 0 this time, and the result became interesting. If the external force is said to be minus g, then the results recall the previous figure, this one, due to particles being pushed out to the boundary of the channel that previously used. So the form of the upper boundary is the same that in symmetric channel. That's why the form of the curve and also the simulation points looks the same, obviously, with at different scales. And also, we can see that if the force is strong enough, the effective coefficient drops to 0, okay, trapping or catching the particles. If the force has now a plus sign instead of where the opposite sign, the coefficient tends to a possible maximum of the value, that is the 0. Okay, remember that for these simulations, the 0, or the bulk diffusion constant, was taken to be 1. So we can modulate the coefficient diffusion. Just know that these plots for symmetric and asymmetric was drawn using a logarithmic scale, and also with the inverse in the independent variable of x axis. It's the inverse of the force. Now, let's get to the conclusions. It is possible to follow Regalen-Rouvier and Kalina's suggestion to write the diffusion coefficient as an approximate interpolation formula, which in some cases it became convenient, and also we can recover previous results. It doesn't matter where if we take our main result with a complete expression with this hyperbolic function stuff, or the interpolation formula. The Brownian dynamic simulations and equations 5, 6, and 7 are in excellent agreement in both cases, symmetric and asymmetrical cases. For the symmetric case, also reproduce the predicted behavior found by other methods, like one presented by Brodage and Schmidt. And the new diffusion coefficient generalized previous results, reporting literature, and this can recover as limit cases. Doesn't matter if we take just equation 5 or the interpolation formula represented in expressions 6 and 7, we can reach any of the previous results. Now, if the force G goes to plus or minus infinity, the equation 5 predicts a unidimensional or one-dimensional behavior that looks really promising in order to achieve a particle separation, obviously choosing the appropriate boundaries of the channel, but we can achieve this particle separation and also trapping the particles. Saying this, the diffusion coefficient tuning is possible. We can modulate. And this modulation and switching of external feed could be used to achieve this. Also, and I said previously, the boundaries must be chosen appropriately to achieve this. Now, what's the further work? Well, we're thinking to extend this model to include the influence of external forces in an arbitrary direction. This is because we only have a transversal external force and also constant, and a natural continuation of this work will be the development of an equivalent model for 3D tubes, and the inclusion of diffusing biological substances could require a different background, a theoretical background, right? Like anomalous diffusion, exploring an alternative basis to derive a generalized theory must be explored. This because every single result obtained apparently comes from another generalized theory that we cannot discover yet, but maybe using another approach like path integral or something like that, we can develop. We can find another interesting theoretical tools. And these are the references. Thank you very much for your time and attention.
Thank you so much, Ivan, for your presentation. So now it's open for questions. No? Ivan, I have a question. Could you back to the results, to the graph that you are showing? What? I guess that it's perfect. Okay. I mean, did you study the effect of to increase the size of the crest or the amplitude in order to see if there is a change? So I mean, try to see what is the effect of the boundary, because sounds like only there is like an effect normal to the surface. I mean, what is the effect to have like a sinusoidal shape of the boundary? What do you say?
So if we play with this boundary, we can see some really some effects. If we take this amplitude, for example, and we open this this boundary, or we translate the upper boundary more up in the y direction, we can see that the confinement effects over the diffusion of the random walkers is going to disappear. Remember that that for the Brownian movement, or Brownian movement is not efficient traveling long distance. So if we separate the boundaries, we cannot. It is possible that we cannot see any of these effects, and the effective diffusion coefficient tends to be the bulk diffusion coefficient, or constant. I think that your question was if we take this this boundary and we turn to
let me try to reformulate the question. I mean,
please.
Maybe if you propose like a delimit case defining like the amplitude as such as, I don't know, alpha or any letter, and that value tends to be 0, you recover like a Jones simple channel, okay? And then you start to increase this parameter in order to have a more amplitude or less,
okay.
And the press maybe is higher.
Okay.
How is the effect of the boundary? I mean, how change the diffusion, the effect diffusion?
Okay.
In order to figure it out.
I think I got it now. It will depend in 2 parameters. One will be the amplitude of the crest, and the second, the period of this one. We need to find a relation that will allow us to tune the effective diffusion coefficient as we like, but and I don't have a mathematical analysis about it, but if we add more, if we increase the amplitude of this without varying the length of the period, we are going to see that the particles is going to be trapped more easily, because the effect of the crest is going to act like a kind of potential, a sink potential, kind of, because this is going to be to reach upper, and the force is going to be push all the random walkers to upstairs. But in order to escape from that curve, it's going to need to be traveled a little more, but the same force that is been pushing up those particles doesn't allow to escape so easily. So it's going to act like a sink, kind of. Of course, if we maintain this this period length the same, and we only increase the amplitude. Okay. That's what I meant when I said that, yeah, that the force and also the boundaries of the channel must be choose wisely in order to get the traffic, the trap or separation effects using this kind of expressions. I don't know if I answer your question.
Yeah, yes. Thank you so much, Ivan. We have a question from Pavel. Let me give a permission to talk. Pavel, can you hear us?
Yes, thank you, Julio. And thank you, Carlos. Sorry, Ivan Pompa, for your talk. My question is a little bit related with the question before by Julio Armas, related to the boundary conditions. So my question is basically, how do you describe the boundary, mathematically speaking, the boundary conditions that you use in the diffusion equation in order to perform this projection method? And how do you assure that these boundary conditions, how do you implement in the Brownian dynamic simulation these boundary conditions?
Okay, well, let me get back to the projection method. Now, the first thing that we need to do is take, in this integral, we are going to obtain some relations that we also are some recursive relations about the boundaries and the flux over that boundaries, and that allows also to obtain this diffusion coefficient. Also, at the end, we need to take those boundaries and substitute right here in order to obtain the corresponding diffusion coefficient. Now, in Brownian dynamics, that we need to take is this, and the actual algorithm to solve this is taking the Langevin overdamp equation and add an external force term, and we are solving by finite difference by means of the Euler-Murayama method. Also, it has the same form that simple Euler, but I think the background, the mathematical background, is a little bit different, but the result is just the same. And for the boundaries, it was to implement a rebound function that calculates the reflection over the boundary, taking the derivative of this function that could be numerically or analytically, and then we calculate the point where the trajectory collides with the boundary. We take the derivative, and then with geometry we calculate where this is going to be the rebound of the particle. I don't know if I asked your question.
Yes, that was certainly the answer. Thank you very much.
Thank you, Professor, for your question.
Thank you, Pavel. Someone else have a question for Ivan? Well, thank you so much again, Ivan, for your presentation. And with this, we finish the second day of the meeting. Francisco, Eric, you have some information to give? Paco, about the gather or something?
I open a gather town, how you say this? A gather town session in order to have small meetings or meetings with just one person. You can use that application to meet, just like the last year. Okay, so I will put the link in Twitter just in a couple of minutes. Okay, or yes, yes, that's what we.
How is the link, Paco, for the gather for the?
Yeah, that's what I'm looking at, but I just lose it out. Let me see if I can have it right now. Ah, wait, I have it. Just give me 1 minute.
Could it works in the chat? If someone wants.
Yeah, and then I put in the chat. It's better, right?
Yes, I guess. But the chat for everyone. So I mean,
Yes,
yeah, I
yes,
can
yes.
see, everyone can see the chat now.
Copying by link. Let me just give me 1 minute
Because,
here. So do you see the link?
no, I guess you have to change to send for everyone. Oh, let me try to do it.
Host and everyone. Okay, yes.
Okay.
So it's here.
Yes.
So please use that link. I sent two links, but they send you to the same Gather tab.
Okay, thank you. Well, for everyone, again, this is we finished the speaker sessions or the oral presentation sessions for this day. Tomorrow we will start at 9 a.m. Mexico time. So have a great afternoon. See you later. Bye-bye, everyone. Thank you for attend the meeting. Thank you, Ivan. Thank you, Jose. Thank you, Carlos and Fernando.
Thank you so much. See you.
Thank you.
Thank you.
Thanks for the time.
You too. So I'm going to close.